Hello, my name is Chad Morse, and I serve as the Assistant National Dams Program Manager for the U.S. Forest Service. This presentation introduces a probabilistic human consequence model designed to better represent transient populations in rapid rise events, particularly for dam failures and flash floods. The uniqueness of the model is that it estimates likelihood of exposure without modeling warning and evacuation. The primary objective is to establish a method for determining both likelihood of life loss and the number of people potentially exposed to the hazard. Current Federal Emergency Management Agency dam safety risk management guidelines define risk as the product of the annual exceedance probability of failure and the magnitude of the resulting consequences for a specific scenario or cumulative probability over all likely scenarios. The International Committee on Large Dams, ICOLD, defines risk as the probability and severity of adverse effects on life, health, property, or the environment. This proposed methodology aligns with the ICOLD perspective by explicitly determining the likelihood of consequences and potential exposure. Since the publication of 2012 FEMA risk management guidelines, the dam safety community has increasingly treated likelihood of failure as equivalent to the likelihood of consequences. This trend limits progress in consequence science as many key explanatory factors for life loss are overlooked when failure likelihood serves as a surrogate for consequence likelihood. Additionally, current consequence assessment practices emphasize on non-transient populations and rely heavily on warning and evacuation assumptions to estimate life loss. These assumptions are not appropriate for consequence analysis in hazard potential categorization or risk assessments, particularly for rapid rise events where available reaction time, not formal warnings, drive survivability. The approach proposed here provides a more precise, transparent, and robust framework for consequence analysis, strengthening both hazard potential categorization and risk assessment processes. Historical flood fatality data from the United States and Australia consistently show that more than 90% of the deaths occur among transient populations, including people in vehicles, on foot, and in campers. Research further demonstrates that fatality rates rise sharply as available reaction time decreases, underscoring the importance of incorporating both transient population exposure and time to react into consequence analysis. This need is especially critical for dams with lower estimated consequences, where limited precision in likelihood estimates reduces the usefulness of risk assessments and incremental consequence evaluations. These limitations disproportionately affect state and land management dam safety programs, which typically oversee dams with smaller downstream populations, whereas programs managing large consequence inventories are less sensitive to likelihood estimate precision because of the inherently greater exposure. People routinely travel and recreate on roads, trails, parking areas, day use sites, and campgrounds located within dam failure and flash flood hazard zones on the U.S. Forest Service lands. These intermittently occupied transient populations are largely overlooked in federal consequence analysis guidance, including hazard potential classification and dam safety risk management, despite consistently representing the highest proportion of flood-related fatalities. Forest Service lands are highly susceptible to rapid rise events where water levels can increase abruptly. This measurable factor affects survivability. When transient populations and rapid rise dynamics are excluded from consequence analysis, uncertainty in life loss estimates increases, reducing our ability to meaningfully assess the likelihood of consequences. Current guidance and tools do not provide a clear method of estimating who remains within the inundation area during a failure event, nor do they incorporate the dynamics of rapid rise events into loss of life estimations. Instead, they generally rely on exclusion-based criteria. For example, guidance often promotes excluding populations with intermittent occupation. However, removing these groups from analysis rather than quantifying their likelihood of presence and associated severity reduces the precision of consequence estimates and limits the ability to make informed, risk-based decisions in resource-constrained environments. Additionally, current approaches do not differentiate between locations where loss of stability occurs within minutes and locations where water levels rise over hours or days. The widespread use of exclusion thresholds, such as omitting low traffic roads or non-residential areas to simplify analysis, reduces transparency, weakens defensibility, and undermines the ability to prioritize based on true risk. Life sims and RSIMs generally attribute life loss to two primary factors: the amount of warning and evacuation time available, and whether individuals experience loss of stability or submergence during the peak of the flooding event. While warning and evacuation are vital for emergency response planning, they should not be assumed in hazard potential categorization or risk assessments. Their effectiveness depends on highly uncertain elements such as issuance, delivery, dissemination, activation, communication, and population response, which can't be reliably guaranteed across scenarios or vignettes used in consequence analysis. Loss of stability is a well-supported predictor of life loss, but is inherently conditional. It only occurs when people are present in the inundation zone and are unable to escape or be rescued. Without incorporating these presence and escape-related factors, estimates of both likelihood and severity of consequences becomes less precise and less defendable. LifeSims is an agent-based model which models warning and evacuation for likelihood of exposure, where this proposed method models exposure through likelihood of occupation during the failure event and ability for escape and rescue based on time to react to the imminent hazard. When warning and evacuation are disabled in LifeSims, the model no longer accounts for likelihood of exposure. RSIMS, on the other hand, removes populations of infrequent occupation before estimating fatality likelihood and therefore does not evaluate exposure probability based on any contributing factors. Instead, it provides fatality rates for shelter-in-place conditions both with and without warning and evacuation. Starting with the color-coded definitions at the bottom of the screen, a loading event is a natural or human-induced event that imposes stresses on the dam, for example, rainfall, snowfall, wind, and earthquakes. A dam failure is when a dam breaches and sends a breach hydrograph downstream, which changes form as it loses energy. Occupation of exposed locations is when people are present in the exposure area at the onset of the event at an exposed location. Escape or rescue is the successful self-escape or assistance after detection or initial exposure, assuming no warning and evacuation prior to the arrival of the flood wave at the potential exposure location. Assessing for the probability of no escape or rescue addresses the dynamics of rapid rise events by accounting for the time to react to imminent hazards. Instability occurs when exposed populations lose stability in whatever state they are in, which could be on foot, in vehicle, or in a structure. Under deterministic analysis, the conditional probability of loss of life due to instability is estimated as 70%, consistent with the expected value of the high hazard zone fatality function used in USAID's LifeSims. The chain rule of conditional probabilities makes it possible to multiply all 5 components shown left to right in the boxes at the top right of the screen to obtain the overall conditional probability of loss of life. The probability is calculated as the probability of a loading event occurring multiplied by the probability of dam failure multiplied by the probability of occupation multiplied by the probability of no escape or rescue multiplied by the probability of loss of life given instability, with the sequential chain rule of conditionality for each factor. Current methodologies primarily address only the first 2 elements, loading and failure. And the final element of loss of stability, as shown in the middle of the screen. They generally do not incorporate the likelihood of occupation, which is essential for evaluating transient populations whose presence is intermittent, nor do they account for the likelihood of no escape or rescue, which depends on the available time to react during rapid rise events. As shown in the notes box in the middle of the screen, both factors are necessary to accurately represent the dynamic nature of a flood. Most existing approaches instead rely on warning and evacuation assumptions. However, warning and evacuation should not be presumed for hazard potential categorization or risk assessments because they introduce substantial uncertainty and can't be a guaranteed capability. Occupation likelihood during a hazard event is estimated within separate time blocks that represent the seasonality of hazard event and occupation. This is typically over seasons, months, days, hours, or minutes to account for variance over the entire year. The summation of all probabilities of occurring in time blocks must equal 100%. Time block share of the hazard events estimates the percent of hazard events that support annual exceedance probability estimates that occurred within the time block. NOAA Atlas 14 seasonal information can support estimation of likelihood values within time blocks for rainfall events. Occupancy during time block is based on records of historical site use and geospatial information such as atomized mobile device locations. Satellite-based systems can also enhance coverage in remote regions. Streetlight Insight web platform utilizes connected device data to monitor vehicle, transient, bicycle, and pedestrian traffic counts virtually anywhere. This approach to estimating occupation during hazard events would apply to all intermittent occupation locations except routes that are open all year. In that case, only likelihood of getting engulfed or entering floodwaters would be considered. When the route is closed part of the year, you would perform probability of occupation given the hazard event and multiply it by the probability of being trapped plus probability of entering floodwaters as discussed on the next slide. Routes such as roads, railways, and trails require additional analysis because exposure can occur through two paths. Individuals may become trapped, engulfed by rapidly rising water, or they may enter floodwaters either intentionally or unintentionally. The trap component is driven by factors such as peak groups per an hour, travel speed, and the length of inundated roadway or trail segment. Values represent both the likelihood of presence and the number of groups potentially exposed. The entering component is supported by research showing that approximately 13% of mid-sized car drivers may attempt to drive through floodwaters at depths that could cause vehicle instability. The combined likelihood is calculated as the probability of occupation multiplied by the probability either becoming trapped or entering the floodwaters. Reliance on AADT, average annual daily traffic-based exclusion thresholds, can significantly underrepresent vehicle and route users in risk assessments, and important issue given that more than half of the flood-related fatalities occur in vehicles. The no escape or rescue factor is governed by the time to react to an imminent hazard, which represents the time between initial inundation and the point at which loss of stability or submergence occurs. The proposed subjective equation and graph shown in the lower right provides a severity scale. Very low rates of rise allow several hours for a 2-foot increase in water depth and correspond to a high escape likelihood, while very high rates of rise allow less than 2 minutes, resulting in very low likelihood of escape. Research by Dr. Jonkman identifies a sensitivity threshold near 0.14 feet per 5 minutes, marking the transition where the potential for life loss increases substantially. A 2011 Homeland Security Consequence Analysis document proposed incorporating rate of rise as a hydraulic characteristic to estimate time available to react. However, this concept appears to have been ahead of its time as it is still not widely applied in consequence analysis for rapid rise events. Future research of historical rapid rise flood events and subjective interviews could support further verification of likelihood estimates. Time to react can be estimated through commonly used hydrodynamic modeling tools. Downstream consequence analysis typically extends 10 to 50 miles downstream depending on the flood wave volume and available storage. As the flood wave travels downstream, it loses energy. The rising limb of the breach hydrograph flattens, and in turn, the available time to react to the imminent hazard increases, reducing the likelihood of life loss with increasing distance from the dam. The proposed model integrates seamlessly into existing hazard classification and risk assessment processes without requiring those frameworks to be replaced. For hazard potential classification, the method identifies the highest probability of life of loss among all potential exposure locations under the worst case reasonable failure or misoperation scenario. This aligns to FEMA 333 expectations for classifying a dam based on realistic probable consequences. For risk assessments, each exposure location contributes a weighted value calculated from its probability of loss of life and its proportion of the total potentially exposed population. Summing the contributions across all locations produces a comprehensive dam-specific estimate of the likelihood of life loss. By replacing subjective exclusions with data-driven likelihood and incorporating the dynamics of rapid rise events, this approach improves transparency, strengthens defensibility, and supports clearer prioritization of resources across dam inventories. The proposed model introduces a more robust, probabilistic approach to estimating risk, rather than relying solely on the likelihood of failure, which is often used as a surrogate for the likelihood of life loss. Although the current formulation is deterministic, it can readily incorporate probability distributions for key inputs and produce confidence ranges for loss of life estimates. These ranges can be displayed using box and whisker symbols for each dam showing upper and lower bounds, quartiles, percentiles, and weighted averages. Each symbol shows the range of likelihood of loss of life for a dam or exposure location for a single scenario or a cumulative estimate for all probable scenarios. Incorporating additional explanatory factors for likelihood of loss of life into the frequency of exceedance axis of an F&N chart would enable more realistic estimates of consequence likelihood. Additionally, the frequency of exceedance can illustrate the weighted likelihood of life loss over the service life of the dam, making the results more intuitive. For example, stating a 5% chance of exceedance over 50 years is easier to interpret than reporting a fractional percent chance for any single year. Displaying potential exposure numbers on the x-axis rather than modeled consequences alone additionally increases transparency and clarifies how consequences were estimated. This approach can also be applied at an individual dam level, producing F&N charts that reflect the likelihood of loss of life across all specific exposure locations for that dam, rather than only at the inventory scale. These are the references used in this video and article. Thank you for your time. Thank you for all the people, including my supervisor, for supporting me. God bless, and I hope this helps encourage continued discussion around new approaches for illustrating estimated risk.